to welcome you all to this week's DTM seminar. Today's speaker is Barb Cohen from NASA Goddard Space Flight Center. Barb originally grew up in upstate New York and got her undergrad degree in geology, not biology, geology at Stony Brook. And then went to University of Arizona where she got a PhD with Tim Swindle in planetary science and gained her unhealthy love of noble gases. I guess they're all right.
For some
and then
things.
moved on to, has been at NASA for many years, first at Marshall Space Flight Center in Alabama, and very recently moved to Goddard up here in Greenbelt. She's been involved in a wide variety of cool NASA projects. She's driven Mars rovers for years. She's PI of a, I think you're going to talk about Lunar Flashlight, right?
I'm not, actually.
Oh, she's PI of a really cool little CubeSat mission to the moon called Lunar Flashlight, and a bunch of other things. And she's designing and building noble gas mass spectrometers to fly to other planets and this kind of thing, as well as doing measurements in her own laboratory. And she's going to talk to us about the violent early solar system.
Thank you, Larry. Thanks, everyone, for having me. I appreciate being here. So part of this is just some fun review of the early solar system and planetary geochronology, which is where my first love is. And then part of it in the back is going to be a little bit of an advertisement. And as Larry said, we just moved here. And I know some of you, I've worked with some of you, but I hope to know more of you and work with more of you. So if you're interested in any of these pique your interest, please let me know. So geochronology, I'm sure I don't have to convince you of the value of geochronology, but I'm going to do it anyway. Geochronology, a lot of times I get pushed back on saying, well, okay, you get rock ages and that's nice. But rock ages, it's not just rock ages. What we're really talking about is the time evolution of planets. So when we look at rocks as geologists and we say whether they're rolled around in dunes or they're formed in water or wherever they were formed, geochronology is what puts those events in order. And then geochronology is also what ties those planets to each other. So what was happening on different planets at different times, and therefore what were the solar system dynamics that were happening across all planets at that time. So some of the things that we look at in our lab are when did the outer planets migrate and the asteroid belt lose its mass? We'll come up on that. That's a model for solar system bombardment. Lots of things whizzing around the solar system and crashing into other bodies. We really want to understand that. How did it affect a whole bunch of inner solar system planets and maybe outer solar system planets? When was Mars warm and wet? Larry said I drive rovers. I don't actually drive the rovers. I'm on the science team. I tell the rovers where to go to get data that I want to know. We want to know when Mars was warm and wet. This is the #1 question that comes up at press conferences. I don't know if you know that Mars once had water. Sometimes we discover it again and again. But every time there's a press conference and we say Mars once had water, there's invariably someone from the press who will get up and say, when was that? We don't know. We don't know when that was. We don't know how long water may have persisted on the surface of Mars. And we don't know what the planetary history was at the time that that was going on. That's a really important question. What was going on in the rest of the solar system, particularly for the Earth? So how long did it take life to arise on Earth? What were the conditions like in the liquid water persisting on the Earth? How do we extrapolate that to other planets? How long were planetary heat engines active? So these are things like lava flows. And here I have a picture of the moon showing some of our very, very young lava flows on the moon. Maybe I'll show you that. Well, anyway, these red ones are very, very young, like billion and a half years young. That's really, really young for something like the moon, which is a one-plate planet that lost all its heat very early in solar system history. But obviously, planetary heat engines are still active on different planets. Mars, very, very young. Venus, maybe still today, maybe still having active volcanism. So we want to know how these planets formed and evolved and what their heat engines were doing. And the ages of the rocks help tell that story. Something that I'm not going to talk too much about, but something that I've recently got involved in is surface exposure ages, particularly for Mars. And this is something that we can do with Mars Curiosity. I'll touch on it a little bit. We've got some upcoming experiments with the SAM mass spectrometer that can get at surface exposure ages on Mars. And that can tell you about the denudation history or the erosion history of a place, as well as, for meteorites, of course, it's something that we've been doing and you guys do here for a long time is the exposure ages as well. So how things moved around and how things became exposed. So these are all really fun and interesting projects we get to do in geochronology, even though, yeah, okay, it's just a rock age. So this is my fave astroplot. If you go and look at Twitter, there's a hashtag out there, fave astroplot. This is mine. And it's because this is the only place, the moon is the only place in the solar system where we get to have surface ages correlated with radiometric ages. And this is incredibly powerful. This forms the basis for our understanding of ages of all other planets because we don't have rocks that we picked up and we know exactly where they came from. Meteorites come to us from all over, but we don't know exactly where on those terrains they came from. But here you can have the crater production rate on the y-axis and the actual radiometric age on the x-axis, and you can correlate those two. And what that means is you can extrapolate that to other places where you don't have a radiometric age. You can count those craters, and you can say, all right, the crater density says wherever I am along this curve, that's an absolute age. But you need to calibrate that. So for the moon, we have that calibrated up to about 4 billion years, where you can see all of these gray things with these well-dated surfaces. These are mare surfaces, and in some cases, crater surfaces down here. And so those are well-dated surfaces. And then you see these lighter gray ones up on top, Apollo 14, Apollo 16, typical highlands. Surface age not well known. That's because the moon gets saturated with craters. Every new crater that forms wipes out another crater, and so you don't have a good crater count anymore. It's just saturated. So before about 4 billion years on this plot, we don't have good surface ages, and we don't have good radiometric ages. So that's where my interest has been lying for a real long time, is what was going on for sort of 4 billion years old and earlier. So for the moon itself, one of the things that we think about is sort of what was the bombardment history like? What was the impact history like? If we just came up with a model for how the solar system formed and we put the moon inside of it, what would the bombardment history be like? And most things come up with sort of a variation of this kind of declining flux. And the details of it aren't important, the steepness or when it tails off. But you can think about the solar system forming. We know that planetesimals had to get together, and they had to form bigger and bigger planetesimals. And then you had sort of big planetesimals that were winging their way around the solar system and crashing into each other. We have a lot of evidence for that, right? We have Uranus tilted on its side. We have Venus in a retrograde orbit. We have us and our moon, which we think formed in a giant impact. So we have a lot of evidence for things winging their way around the solar system and crashing into each other. And where you have big things, you have a myriad of small things. So we sort of think of this declining flux, this sweep up of the solar system went on, and eventually we don't have a lot of things hitting us now, so eventually it had to come down to nearly nothing. So this is kind of the thing that we thought we would see when we looked at impact rocks on the moon. So when we went with astronauts and we picked up rocks and we saw things that we could show were formed in an impact event. So they were remelted. Maybe they have a lot of siderophile elements in them that come from meteorite input. Maybe they have particular textures or particular compositions that are a mix of several kinds of target rocks. So we know that they were melted and crystallized in a large impact event. So when we date those, we thought we would get a lot of them that were really old. That's when a lot of impacts were happening. That's when you would create a lot of impact melt that's old. And then you would have a declining number of impact melts as you went on in history. And of course, I wouldn't give this talk if that's actually what happened. That's not what happened. What happened with the Apollo samples, and this is from a pretty old compilation now and probably needs to be updated, but it's still pretty, there's still a really good compilation of what had gone on, at least through 1995, and particularly in the heyday of the Apollo samples. So these are just impact rocks. So these aren't all rocks. Lots of rocks are older than this on the moon, particularly things like the Genesis rock that tell us the age of the lunar crust, the age of lunar plutonic activity, magmatism on the moon, metamorphosis on the moon. A lot of those come out in here. So I'm not talking about those. Those exist. We know a lot about the formation and evolution of the moon that way. These are impact melt rocks. So these are the things that have been created in impacts and tell us about the impact history of the moon. And they all pile up right here. So this is something that we didn't expect, that a lot of people have spent a lot of time and energy on. It's variously called the lunar cataclysm. In this case, it would be the lunar cataclysm. It's just the moon. It's been expanded to be called the late heavy bombardment as well. That's sort of a more generic solar system-wide version of this. So you'll hear me go back and forth between cataclysm and late heavy bombardment. Here I'm meaning them sort of synonymously. As time went on and people got more and more into the game, including me, I thought I would go on to fame and glory by finding the impact melt rocks that were here in lunar meteorites. I thought, well, lunar meteorites, they're a more random distribution of things. They're far away from the places that Apollo astronauts and the Lunokhod rovers picked up samples, and I thought, oh, I'm going to find them. They're all in those lunar meteorites, and no, I didn't find them. Lunar glasses, a lot of different kinds of materials, reanalysis of Apollo rocks, updating decay constants furiously, trying to make those older and older. And so with all the data that I could find sort of fairly recently, you can still see that they pile up around 4 billion years. You've got some going on down here, but you get a big pile up, and then you get noticeably nothing up here. So it's really important. That's telling us that we are not understanding the early history of the moon in a way that's consistent with what we know about the solar system. So the classic cataclysm, as it was formulated in the 70s, actually came out of uranium lead. And so uranium lead, of course, you can get a concordia and a discordia, and so you can say when the sample crystallized and when it was disturbed, when it leaked lead. And so the original came not from necessarily impact melt rocks, but from these rocks that leaked lead at about 3.9 billion years ago. So they were formed at 4.5. They still had that signature of formation, and then they leaked out lead at 3.9, and that's a metamorphic event. It's something that caused them to heat up and leak the lead out. But also, rubidium, strontium, argon ages all corroborate this story. And I sort of mixed them all up on the previous graph. They all corroborate that story. They all have something going on at 3.9. We can't really tell if it's something that looks like this, which is just a spike. Here's your impact flux again and your time. Also, just to keep you on your toes, sometimes time here is 4.5, sometimes it's 0. So x-axis these change a lot. But here's 4.5 billion years ago. Maybe you had a declining flux, and then you have a spike of impactors. What we can't tell is maybe you had many spikes of impactors. Maybe you had, instead of a declining flux, maybe you had almost nothing happen and then a spike. Well, we can't tell the difference between those two anymore because all we have are these ones at 3.9. But interestingly, the earliest isotopic evidence of life on Earth, this is actually pushed back a little bit from this slide. It's up at about 4 billion years now. Fossils don't come in until about 3.5. We don't have a lot of old rocks on the Earth, too. Why is that? We have plate tectonics, and we have recycling, and we have wind and water and rain. But there's very, very few rocks that are older than this. And so one of the hypotheses could be that we bombarded the crap out of the Earth, too, and that we don't have any of the old rocks that from that era anymore either. So it's coincidence right now. A lot of people are working on this as well. But I can tell you that every crater that you see formed on the moon had a counterpart here on the Earth, right? So something coming in from infinity, the infinity is not going to care whether it hits the Earth or the moon. It's a single system until it gets right up close. And then the Earth has even a larger gravitational cross-section, so statistically a few more of them will go to the Earth. So when you look up at the moon and you see the giant basins, and you see all these craters, at one point the Earth had all those craters too, and probably more. So we do know the Earth got pounded as well, and we don't know really what that would have looked like on the Earth at this time. These earliest rocks are metasediments. So we know we had continents. We know we had, wind and rain and water making sediments. So we think that we think that the Earth then was pretty similar to the Earth now. So you would have bombarded the Earth in that state, and that would look a lot different from the way we see it now. Okay, so on the moon we have this giant basin called Imbrium up here in the northwest corner. It's the biggest basin. It's stratigraphically one of the younger basins, the youngest on the near side. And so we've dated that a couple times, notably with Apollo 12 and Apollo 14 rocks that got thrown out of Imbrium. And it's about 3.92 billion years. That's our current best estimate. But it used to be about 3.85, and that's important for my next slide. But currently it's about 3.92, and so that's right at that same time, right? That could be what's causing all of those impact melt rocks to be that age, and particularly because when you look at, this is a thorium map of the moon that we got from Lunar Prospector. When you look at the difference between these two, you can really see that Apollo 12, 14, 15, all these things that we looked at for Imbrium are all in this thing called the prosolarum creep terrain. Creep stands for potassium, rare earth elements, and phosphorus. These are very incompatible elements. They're things that don't like to go into the crystalline state. They like to stay in the melt until the bitter end. Also things like thorium, uranium, your heat-producing elements, and a lot of your radiogenic parent elements are in this creep terrain. And the idea is that when the moon formed and it was molten and it crystallized, because of the particular composition of the lunar magma, when it started to crystallize, you had mafic elements like iron and magnesium and stuff go into your olivines and your pyroxenes, and they're more dense in the liquid, so they sink to the bottom of the package. Things like aluminum and calcium go into feldspar, and they float on top of this liquid, actually. And so the crust of the moon is made out of this feldspar, that's this cumulate flotation crust. But all your incompatible elements that don't like to go into crystals stay in the middle. They get sandwiched in this creep layer. And they get exposed when you have a really big basin, excavate under the crust to that creep layer and throw it out onto the surface. So that's the genesis of this prosolarum creep terrain, is this Imbrium impact. And so all of these rocks that we picked up at Apollo 12, 14, 17, these ones that I said gave us the age of Imbrium, they all have really high potassium content, so they're good for potassium-argon dating or argon-argon dating. They're good for uranium-lead. They're full of uranium. So these are all really nice things to date, and they're very abundant. And so it could be that we're just very biased, that we have a biased collection from their Apollo astronauts, and we have a bias in ourselves and in our laboratory techniques that we date things that we can that have these radiogenic parents in them. So that is one thing that's been floating around for a long time. Larry Haskin actually advocated this a really long time ago, that everything that we've dated is from Imbrium. But what about Apollo 17? You can see Apollo 17 hanging out here outside of the prosolarum creep terrain. So let's look at Apollo 17. Apollo 17 collected impact melt breccia samples, and their whole goal was to try to get at the Serenitatis impact. So the Serenitatis impact is close by. We wanted to get another big basin. Like I said, these ages go back and forth a little bit because of just, like I said, the way that we do our corrections and the way that we do our decay constants. But at the time, when we dated these, they were 0.03 billion years before Imbrium. And so what that set up was this thing called the cataclysm, where we said that Serenitatis and Imbrium and several other big basins, it turns out to be about 20 big basins, all formed in a very, very short period of time, right? 20 million years, 30 million years. That would be very unusual. You'd have to have a lot of big impactors coming in 20 million years. Dynamically, that's very unsatisfying. There's not a lot out there that can do that. And so, okay, not everything we picked up was Imbrium, and this shows it because we have Serenitatis. Right. And then, not really. Okay, so let's talk about Apollo 17. There's been some really interesting work done with Apollo 17 recently that show that maybe it's not Serenitatis after all, and maybe we're going back to this thing where it's Imbrium again, even though it's really far away from Imbrium. So here's the Apollo 17 landing site. It's in this Taurus Littrow Valley. We have two massifs, North and South Massif, and these are big chunks of broken up material that we thought came from the Serenitatis impact. So those big impacts throw out a lot of material. Sometimes we think of nice, smooth ejecta blankets. That's not reality. It's close to reality, very close to the crater, but then farther away from that, you just get massive chunks of stuff that's discontinuous. So these massifs were thought to be Serenitatis. They're overlain by this unit called the Sculptured Hills, which is probably Imbrium ejecta. But we didn't know that at the time. So Deborah Hurwitz did some really nice jobs with the LRO imaging, and you can see it there up in the top right. It's hard to see here, but if you go look at her paper, it's really clear. These are boulder tracks. Those dotted lines are individual boulder tracks. So from the Apollo site, they didn't go up onto these massifs and sample them like you would want to do. There's no obvious benches that are outcrop necessarily, and so they sampled the boulders that had rolled down. And then said, okay, we see that they have boulder tracks. They came from up higher. And so Deborah went back and actually correlated them where they were in the massifs. And so we think those boulders came from those massifs. We think they came from specific horizons in those massifs. And so some people have interpreted those as bedrock massifs that we're sampling them from. When you do that and you look at the ages, though, here are the ages from some of those massif deposits. So these are all Apollo 17 samples. And age is on the y-axis here, and it goes from 3.8 to 3.95. So that's a pretty big range when we're talking about just the difference between those two ages that I told you before, 3.92, 3.85. That's a pretty big range. These are all from those boulders. So if you want to say that this is the age of the Serenitatis impact, where do you put that line? Now, Jack Schmidt, who I'm not going to argue with in public because he was an astronaut and he picked these rocks up, he argued that the Serenitatis impact was just right after Imbrium. He argues that Serenitatis is younger than Imbrium, and you can see that in these rocks, and that you have an older age that's from Crisium. To my eye, this looks like a mixing line. This looks like you have inherited argon, that you've got some young ages and you've got some old ages, and they're sort of mixing themselves up together. And that might be what you expect from a breccia that's got an impact origin. So it's a breccia that's got a lot of debris. Some of it gets reset in the impact and melted. Some of it is cold, clastic material that does not get reset. And so to me, this looks very much like a mixing line, and I don't think you can make a clear assignment based on these data. So I think that, oh, and also, also these Apollo 17 impact melts end up being very thorium enriched. So you don't see that from the surface. You don't see it in that surface expression of creep. But these impact melts, when you look at them, are enriched in thorium. They have incompatible element abundances very similar to some of those other Apollo 12 and 14 samples. It pretty much says they're Imbrium. So Imbrium, I think, is a really outsized influence on our sample collection. I fought this interpretation for a really long time. I fought with Larry Haskin. I fought this and said, no, you know, we have really fine differences in ages. We have really fine differences in chemistry. That can't possibly be true. But more and more, I'm coming around to this idea, too, that ejecta facies are really bad places to look for trying to get a hold on the basin age itself. So if I'm far away and I just get something that's thrown to me, it doesn't come tagged. It doesn't say, hi, I'm from Serenitatis, please date me. It doesn't say I'm Imbrium. It doesn't say I'm Crisium. We have to make those interpretations the best we can, not casting aspersions on that work because we do the best we can every time, right? And then when we get new data, we make reinterpretations. So I think that looking in basin ejecta is a really bad place to look for the basin age, and I think that looking on the near side in the Imbrium region is also a really bad place. So I'm not sure that we have a cataclysm anymore. I'm not sure that our lunar samples really are showing us that 40 large basins formed in this small period of time. Now that's interesting because the dynamicists have really gone to town with this, and the earth scientists have really gone to town with this. So we have to look for other things to look at. Let's look at these lunar meteorites. Lunar meteorites are a more random sampling of the moon. They're notoriously very difficult to work with because they have very little potassium. So doing potassium argon dating and very little uranium, so they're very hard to date. When we can date them, this is sort of the age distribution that we get. This was summarized. Simone Marchi did a really nice paper recently. And so here's 4.5 billion years over here, and here we go down to younger ages. And there's just not that many of them. This isn't a histogram. This is a probability diagram, so don't think of it as histogram. But where you see it go up, there's a more probability of having samples that are that age. And so you don't see anything here really piling up at 4 billion years either. You see a lot coming down to younger and younger ages. We had originally interpreted this, when I looked at lunar meteorites, as a tail off of the cataclysm. So you had a lot of things bombarding at 3.9 billion years, and like I said, those are all really big things. Whenever you have a lot of big things, you have a whole coterie of small things as well. And so those take a little bit longer to tail off, and they make smaller and smaller impacts. And I think that's what we're sampling in the lunar meteorites, are much smaller impacts, much more regional influences. So they're not telling us much about what's going on in that region. Katie Joy did some really nice work about looking for really ancient solar wind signatures in Apollo 16 rocks. And Apollo 16 is pretty far from anything else. It's probably got a lot of basin ejecta, but it's mixed in with highlands rocks as well. And so she said, well, you know, maybe some of these really Old breccias with a lot of solar wind, maybe they could have something in them, and I looked at them and no, they don't. They're all still around 3.9. People have really been mining the sample collection, looking for older ages. So now we do have some impact reset ages, 4.1s, 4.2s. You'll see a couple papers where these crop up, but we don't have any really good assignment of what those samples are to an impact event, like a basin, specific basin. So they are in the collection. What we haven't seen is any 4.3, 4.4, 4.5 impact melt rocks. So we're mining and mining and mining this collection, and we're just getting dribs and drabs. Zircon's a great place to look for old ages. They really, really are very resistant. They're not going to leak. They do have damage after a long time, right, because they have their own internal radiation damage. And so people have been looking at lunar zircons as well. Now here it's hard to tell. Sometimes these zircons are in the matrix. So they could be just regular zircons that form in a lava flow, or they could be zircons that form in an impact melt sheet. They could be one and then the other, right? They could have a core of one and then be remelted in an impact melt. So they have sort of a range of ages too, and I'm not going to show you that graph, but they have a pretty wide range of ages from 3.9 up to 4.3. They don't come tagged with their event either, and so we can't use these to say, here's when Serenitatis formed, here's when Nectaris formed. So we're not sure whether these are all Imbrium or not either. So I don't think we can use lunar samples to find these old impact ages. We keep trying. We certainly probably will find one or two. I have no doubt that eventually we're going to find one or two, but we're not going to be able to use that for a really robust lunar history. So let's look at asteroids. If we have something like the lunar cataclysm, and we extrapolate that to what was happening in the solar system at that time, it would be kind of crazy to think that something was only happening to the moon, that we had a population of impactors that only hit the moon or only hit the Earth-Moon system. Very dynamically unlikely. How would you store a population in Earth heliocentric orbit for 600 million years and then have it just crash into the moon and the Earth? So if we think about things that could happen in the solar system instead, if we think about resonances in the asteroid belt, or if we think about populations like the Oort cloud or things like that, that would affect the whole solar system. So we should be able to look in other places and find the same signature. So let's look at asteroids. Again, the same Marchi paper and some work that I did alongside. When we were out here at 4.5, these are just impact ages. 4.5, a bunch of impact ages. That's what we would expect. That's the formation of the solar system, the formation of the asteroid belt. We'd expect a lot of things to be colliding with each other and creating a lot of impact melt. We see it in the asteroids. So something is preventing us from seeing this kind of history on the moon. And then you see this pile up here at 4 billion years, 3.9 billion years. So you see a very, very similar pile up and then a tail off, the same as you see in the lunar meteorites. So even though maybe Imbrium has a real outsized influence on our understanding of the Apollo samples, I think the asteroids really corroborate the story of the lunar cataclysm or the solar system late heavy bombardment. One thing that is interesting out of the asteroids, and particularly Howardites that I worked on, is that the inter-asteroid collisional velocity in the asteroid belt is very low, right? It's like when you're on the freeway and you overtake a car. You may be both moving really fast, but your inter-velocity is very slow compared to each other. So asteroids sort of creep up on each other, and when they collide, they tend to have low collision velocities. Low collision velocities may make a crater, it may make a visible scar, but it doesn't melt a lot of stuff. And when you think about the kinetic energy equation and you've got 1/2 mv squared, it's that v that really adds up. So it's your velocity that really creates a lot of impact melt, which is what we date when we look at these rocks. So to date these things requires things that have a high velocity to create a lot of melt. And so we call those impacts of unusual velocity. That implies a different population of impactors than the current asteroid belt. That's not just current asteroids creeping up into each other and colliding. That's something that's a dynamically excited population. And so that requires some different kind of solar system event to excite a population of impactors and really bring them in and collide in this scenario. Yeah? Yeah, I didn't ignore them. I just didn't talk about them. We don't know what is happening out here. So it could be multiple episodes And I said in the beginning, we may have multiple spikes in the lunar record. We just can't tell. Maybe we're preserving those as well. We don't know. We don't know what that is. You have an idea? No? Okay. If you do, you can talk to me. Chondrites. I like this one. I'm about to head out to Antarctica for my 4th deployment to search for meteorites in the Antarctic. And I like this slide because these are very, very small. You can see the scale. We call them POS. We call them pieces of space. But they're very, very small, ordinary chondrites, ordinary chondrites. And these are the things that when you go out, anyone can tell you that these are things that you hate picking up. And yet, LAP 031173 is one of these that is in this histogram. And these are places that have been impacted and show impact ages. Tin Swindles published these among others. And again, you see on the H chondrite parent body, these impact ages get preserved from the beginning of the solar system. And then there's a relative quiet period, and then they go right back up again. And again, okay, all right, there's details in here that maybe should be explored. But I think the bottom line is that we don't see anything in here, right? We should be seeing those things if there was a lot of stuff going on in the early solar system. We don't. Mars, my fervent hope is that on this field expedition that we get another regolith breccia from Mars with impact melts in it. I like studying breccias. I like studying all the impact melts that you get in breccias. We only have one right now. It's filled with zircons that are pretty old. But Allen Hills 8401, which is our more famous Martian meteorite, or was more famous for a long time, has some really great evidence for crystallization at 4.5 billion years and then shock and remobilization at 3.9. So it's our only age that we have that has a shock age and a remobilization of fluids in all of our meteorite collection that could preserve this, right? Because you have to have something that crystallized before this. So it's the only one that we have, but still the fact that it's the only one we have and it still shows this 3.9 age, that's really, really interesting. Okay, here's zircons on the Earth. People want to find pieces of the ancient crust, and so there's a lot of zircon work, and these zircons are incredibly complex, as you can see here in luminescence. So they've got many, many generations of overgrowth, cores and overgrowth, and all sorts of crazy things going on in the core, breakups and stuff like that. So people have worked really hard on looking at Hadean zircon ages to understand the growth of the crust, the evolution of the crust. But some people would interpret this kind of histogram of zircon ages, and this is many people's works. Here's 4.1, here's 4.5. So even on the Earth, right, we know that the Earth didn't form its crust instantly. We know that there was a growth period, and people have been looking at the growth of continents, and that's probably where you would get most of these zircons. But, right, we have a whole 4.0 zircon history here, and some of these are overgrowths. So some of these are cores that are old, and then they have overgrowth here at 4 around. And so that's something that a lot of people have been working on. I am not super qualified to talk in detail about this, but I know people are really excited about the ability of zircons to hold on to some of these old ages. There are also other hypotheses. Wet mantle can also give you a whole bunch of zircons coming out. So this is really under debate. Okay, I talked a little bit about the dynamicists and how they got really excited about some of these things. One of my mentors was Jay Malash, and he always said, where models and data disagree, that's where science is. So he was one of the first ones to really show how you could get Martian meteorites off the surface of Mars without shocking them to bits. And so, right, we didn't have a way for that to happen for a really long time. Then the modelers came up with a way. One of the things that has really impressed me over my career is that these really small samples that we get ages on drive these giant dynamical models of the solar system. And just since I've been in the business, the amount of computing power that we've had has grown amazingly, and the ability to make high-resolution simulations of the entire growing solar system. And so this is something called the NEAS model. It was one of the first models that really looked at the entire growth of the solar system, and not just the late heavy bombardment. The late heavy bombardment in this scenario was a byproduct of their model. what they were really looking for was how did the giant planets form, and what was their interaction with the Kuiper belt. And so that's what they were really looking at. So in this scenario that I'm going to show you, this is an AU, so the center is the sun, but that first planet there in red is Jupiter. So these are the outer planets. These are the giant planets. And this is the Kuiper belt, these green dots out here. And so one of the things that they showed is that gas giants have so much interaction and so much gravitational influence that these green dots start moving in from gas drag into the sun. They get passed from, and also Uranus and Neptune are reversed here. So Uranus is on the outside, starts on the outside, and Neptune switches places with it. These objects get passed in. They get passed in by Uranus and Neptune and Saturn, and then they get batted out by Jupiter. And so that interaction, there's not a lot of mass going on here, but over time, and you have a lot of bodies, you'll see this whole thing get destabilized, and all of the resonances go sweeping through the asteroid belt that you can't see here. All of these things go crazy. And so this is something that we didn't really understand until we had computer models to be able to show it. So this takes a little while. You can see all of these bodies getting sort of batted around. They're getting passed in and out. It's hard to follow any single one. But they get passed in, and then they get batted out by Jupiter. You can see them leaving the system. And it takes it a little while. You can see it's millions of years for this to happen. Now, models, you can knob to get the answer that you want sometimes. But this is on the order of hundreds of millions of years that it takes. And then you'll be able to see the whole thing will go unstable. And these two outer planets will change places with each other. So this is how we see the current solar system. And so that is one way to get the configuration that we see in the current solar system. And when that goes crazy, all of those things migrate around and crash into things. They're dynamically excited. They've got a lot of velocity. They're going to places they've never been before, like the inner solar system. They're hitting planets. So this was the first model that really, I think, opened up the idea that we could have a very violent early solar system. It's not just something that is gas and dust on a nice, Keplerian orbit, and everything falls out and it's all very quiet and nothing ever interacts with each other. This is saying, no, there's a lot of stuff that's happening. And so a lot of models since then have been shown. There's gas giant migration, especially with extrasolar planets. When we see very big planets right next to their suns, they can't possibly have formed there. You couldn't accrete that gas. But you can form them elsewhere and then drag them in by gas drag and migration. And so jumping Jupiter is one, Grand Tack is one. They have these great names. But all of these are made possible by the advent of computing power and supercomputing power, and motivated by things like this, where we have a dynamical event that we couldn't explain in our own solar system. So the model, the models are the models. It just shows that it's allowed, that we could have these things. So I'm going to go into a little bit of advertising mode for the rest of the talk here, and talk about what the next steps are and what we're doing in my laboratory, in my group. So sample return is something that we've wanted for a really long time. Like I said, I think the Apollo samples are very biased. We're coming around to the view that maybe they're not going to show us the ancient part of the moon. They're not going to show us that old history. Lunar meteorites haven't been able to show us that history. So what we really want to do is find a nice place that we can go where we know the history of the planet or the location, and we can pick up the samples from there. And one of the best places to go is the South Pole Aitken Basin on the moon. It's on the far side of the moon. It's antipodal to Imbrium. There is a little bit of a thorium hotspot there, and that is probably actually Imbrium ejecta that's come all the way around and made a little thick deposit on the far side of the moon. But outside of that, there's not a lot of thorium. There's not a lot of creepy material. It is very mafic. We think that's because the South Pole Aitken Basin is so deep and so big that it's melted either the lower crust or maybe even part of the mantle and incorporated that material into it. And it's a very old basin. And so what that tells us is that if we can get the age of the oldest basin, we'll also get the ages, statistically speaking, of all the superposed basins on top of that. And what that gives us is a full impact history, not just the age of SPA. It's, not just about a rock age. It's about the history of the bombardment. So we'll be able to get all of those out of a sample from the South Pole Aitken Basin. And then, that would be awesome. So we're proposing that. We proposed it to New Frontiers, and we'll hear about those maybe in December. This is our new laboratory facility at Goddard. It's called the Mid-Atlantic Noble Gas Research Lab. It's pronounced moongirl. It's not pronounced moongirl. Although now you're going to pronounce it that way, I know you will. Moongirl is a high-sensitivity noble gas laboratory. The centerpiece is our multi-collector noblesse here, but when we got to Goddard, we inherited a multi-collector helix as well. So our helix is going to be set up to do heavier noble gases, krypton and xenon. Our noblesse is our workhorse for our argon and our neon-argon exposure ages. So these are amazing. I was just telling me earlier that I'll show you some data that amazes me. I set them up to be high sensitivity, and I was like, whoa, it worked. That's pretty amazing. So we are the only NASA noble gas facility. Don Bogard shut his lab down several years ago at JSC, so we are the noble gas facility for NASA. But we are committed to collaborating not just with other NASA researchers, but other researchers with similar ideas and things that we also want to do. So we don't do commercial work, and we won't take your work if it's something that I don't really care about. But if you have something that's terrestrial impacts, or you have something that's planetary, please, you're welcome to come and use our lab. We don't have a fee structure. It's just you have to put us on as co-authors. So I'm going to show you just some quick results from that lab. This is DOFAR 961 that ties sort of those two interests together. DOFAR 961 is a lunar meteorite. It has a thorium, an intermediate thorium signature. So these are not nearly as high as the creep signature on the near side of the moon. This is SPA here. So you can see some thorium hotspots. Those are Imbrium. This DOFAR 961 has an intermediate thorium composition. It's got about 2 ppm thorium. So it's coming from somewhere in the SPA basin. So I was like, great, maybe we don't even see a sample return. I'll just date this rock and we'll get the sample. And yeah, no, that's not true. What we're dating is probably something that's from one of the other basins. But it's a proof of concept to show you that you can use the geochemical signature of the rock. You can relate it to the geochemical signature that we see from orbit. You can tell its provenance. So we're not just shooting in the dark. You wouldn't just get a sample back and just like date any old thing that's in there. You would find the ones with the geochemical signature that you're looking for and date those specific things. When we do that, if you're familiar with argon-argon dating, this is a plateau plot. This is the percent of 39 argon release, so this is a step heating plot, and this is the apparent age. And what we do is we heat the sample up incrementally, and every aliquot of gas that comes out, we measure that isotopic ratio. In a perfectly crystallized rock, these would all be identical to each other, but you can also tell if a rock has had loss or gain or redistribution by things like this little uptick at the end shows a little bit of redistribution. There's a little bit of a downtick in the beginning that shows a little bit of loss, but we had to break some of these rocks up because we couldn't even get 100. We're doing overpressure. We're getting 100 steps out of these things. My lab manager was like, I'm so sick of this rock. Can we just do less of it? These are pretty amazing argon spectra. And they show you a little bit of detail going up and then coming down. We can do, we have very fine temperature control. We can do Arrhenius plots with these. Oh my gosh, this drove her crazy. But what we get out of these is a best fit age of 3.5, so that's not million years, that's, 32 million years. So 3.5 billion years. So I was hoping it would be SPA age. I was hoping it would be 4.4 billion years, but it was not. So it's one of these younger basins that is just turning up the same kind of material, the same composition of material. The SPA melt sheet is probably 50 kilometers thick. It's a really big impact. So we're turning up that same material and remelting it, which is a little bit younger than the uranium lead ages for this rock, but not so bad. Uranium lead is typically a little bit older than argon-argon, just because if this whole thing took a long time to cool, you'd have a little bit lower argon age. So the data that we're getting at is pretty awesome. I'm really pleased with it. So I think we should date every rock everywhere, and I think that means we should have all the sample returns. So sample returns from everywhere in the whole solar system so that we can put them in our lab. Obviously, we can't do that. We would like to do that, but it's a lot of money. So I'm going to give you an example of in situ potassium argon dating, and that's something that I'm working on to be able to put onto rovers or landers. So Curiosity wasn't designed to do in situ potassium argon dating, but it can do it, and it has done it. So we're working on these right now. Ken Farley published the first potassium argon age. It was on this mudstone, and you can see this mudstone up in the upper right corner. that's a true color image. And so you can see that it is not, it's about 2 centimeters across. It's not a homogeneous rock. It's not an igneous rock. It's not something that we would choose to date for our first time on Mars, but that is what Mars gives you, and that is what you do. So we use APXS, which is a surface measurement. So you brush the dust off, and actually we did a rat, or it's not a rat, on MSL. It's a dust removal tool, and then a drill. And you can look at the interior of the rock. And APXS gives you the elemental composition. And from that, you can get the bulk potassium. It's the bulk measurement. We also put that material into the ChemMin instrument, which gives you the mineralogy. It gives you the quantitative mineralogy. So from those two, you can sort of pull out where you think your potassium is sited, in what minerals and in what abundances. And then when we heat it up in SAM and get the noble gases, you can turn that into a potassium-argon age. And so what he got was 4.2 billion years, which is not an unusual age for Mars. We think that a lot of the Martian crust is that old. And we think that's the detrital age, not the authigenic age. It's not the mudstone age, because of this way that we can do the siting of the potassium. We've done 2 more experiments since then. One of them was just Mars gave us crap. It was no fault of the experiment. The Martian rock didn't cooperate. This is going to be reality, right? Some rocks don't cooperate with you. We think that we didn't complete the argon extraction. The SAM ovens do not get to be very, very hot, and so we think we did an incomplete argon extraction. We couldn't get it any hotter, but we don't think all the argon came out, so we think those are not really good ages. But this age is also really nice. Here's another mudstone. We come out with ages that are similar within the uncertainties to the detrital age. And so we think that that mudstone is about 4.2 billion years old. The problem with this is that the crater retention age, this is Gale Crater, and so Curiosity is inside of Gale Crater doing these measurements of detrital phases. Those detrital phases came from the surrounding basalts outside of Gale Crater, and when you do crater counts on that surrounding basaltic plain, you get ages that are much, much younger than that. So you get ages that are 3.6 to 3.8. You don't see that 4.2 age. So there are 2 things going on here, right? One is that that experiment is not how you would do a great experiment to do in situ dating, but the other goes back to the first slide that I showed you, which is our uncertainty in our crater counting age. So we don't have any absolute ages on Mars to tie our crater count densities to. So there's 2 things going on here. We don't really know the crater retention age very well, and that experiment we don't have the capacity to do it any better, so there's a big uncertainty on there. So between these 2 things, we don't know which we need to do. We need to do both, probably, but we don't know what's the right answer here. So the experiment that I'm designing is called the potassium argon laser experiment. It's called Carly. It's not called Kale. It's not called Carl. It's called Carly. And it uses the same instruments that are on Curiosity, but in a better way. So I don't want to do technology development. I'm not a tech person. So I'm going to use ChemCam, which is already developed and flying, and we shoot a laser onto the target and get elemental composition by laser-induced breakdown spectroscopy from the light that comes off. You make a plasma. You excite all those elements. As they come down to their neutral state, they give off characteristic light. It's just like looking at a sodium lamp and seeing that orange of the sodium lamp. You see all the elements and break them down and do spectroscopy. When you're doing that, you're also releasing all of the gases, including the noble gases. And it's quantitative, 1 for 1. Every time you blast that laser, you get that argon out. So you don't have to do it by multiple techniques and hope for the best. The only innovation here is that you have to do it in an enclosed container. So you have to have a sample handling system, and Curiosity does not have this. You have to have a sample containment system so that you can contain your argon and measure it. So that is the only innovation that is in this. So I think it's a good one to put on a first rover or first lander, because it's going to be very highly developed. These are TRL-9 instruments. They're flying right now, and so we can use them to make these measurements. These are 2 pretty young terrestrial rocks that I wanted to just show results on, and these are not great results. And part of the reason is these are all manual valves, and we have to sit there and turn a valve and wait 3 minutes. And so when you do that, you don't want to do a lot of points, so you don't always get a lot of points. But even when you don't get a lot of points, we get ages that are within uncertainty of the well-dated rocks. And so this is not just us. There's a French group that's doing it and a Japanese group that's doing it, and they're all getting the same thing, which is This technique will get ages that give you a 10% uncertainty for older rocks. So this is really good for older rocks. For younger rocks, your uncertainties tend to swamp your age. So this isn't something that we could bring into the field and shoot Eocene rocks with. It's not going to do a great job on that. But planetary samples are all really nice and old, and so this is a really great technique. And so just quickly, the blue triangles are lunar samples, the yellow ones are Mars samples, and the green ones are meteorites. And so when you're on an airless body, you can do a level of detection down here. When you're on Mars, it's up in there. But you can see there's a whole range of rocks that are really, really good for this technique. Shergottites, notably, shergottites are not. I can't lie. I can't tell you I can date the shergottite lava flow. We're not going to be able to do it with this technique. So we have to pick our questions really carefully about where we want to use in situ dating. But it's not that different. It's not that dissimilar from things that you do with elemental composition, or things that you do with isotopic composition, and things that we're doing on Mars now and we're doing with our landers now. They're not appropriate for everything. We pick our questions judiciously. Those are some judicious questions that I will skip over. But if you want to talk about them, and Steve Alardo knows a little bit about this as well. So just to wrap up, I hope I've convinced you that bombardment of solar systems probably happened, although we don't really understand the details very well, and there's a lot more work that needs to be done. It's a really cool example of a post-Apollo view of this dynamic solar system that we could not entertain before we had the ability to look in detail at both samples and models in biology. All of these things work together to bring us this view. And now it's being used to understand extrasolar planet systems. So that's another hot topic about how we can use our understanding to look at extrasolar planet systems. And the bottom line is, if you've got any ideas about these things, or you've got your own ideas that we could use noble gases for, please, please, please come talk to me. We would love to set up a collaboration. Thanks.
We have questions for Barb.
Clear as mud.
Rick.
So the Apollo 17 example you showed, Apollo 17 has a lot of high magnesium sweet sulfur rocks, which have increased characteristics. So what's potentially seeing increased signatures and chemical composition of impact melt doesn't necessarily mean it's total argon.
It's an excellent point.
I'm not a fan of arguing for it.
No, that's true. Yes, but the specific place where they came from, the sort of impact deposit, sure, it could have picked up creep basalt as well, but it's something in that impact melt deposit that came from someplace else. Yeah, good point. Yep, so I looked at some Luna 24 samples from Crisium, and a lot of them ended up being just pieces that were put together, a lot of breccias, and not super useful. Some basalts. Crisium is actually a really interesting place because there's lots of overlapping lava flows. They may not all be the same age. So I know I'm working with Gareth Morgan to look at the radar signature of those lava flows. The other ones, they didn't. There is some work. They didn't turn up a lot of impact melt samples. They are in that big compilation that I showed you. Katie Joy made an appeal at the Meteoritical Society this past year to say, can we open up those collections to doing more of this work? And the answer is probably no. So I think that we may not be able to get more of those either. Another related point, though, is the Chinese are going to go do a sample collection as well. And they have made some deals with both Russia and ESA to be able to work on those samples. But in the US, no. But that doesn't mean that work won't get done. So hopefully we'll see some work come out of those samples as well. Yes, but I can't remember. It's a new, the moon. This is going to the moon. It's going to Bay of Rainbows. They've picked a landing site for it. It's a mare surface.
Well, if there aren't any more questions, let's thank Barb again.
I
Do you know Joy Byer?